Good afternoon, possibly morning, and I suppose even possibly evening, everyone. Can you give me a thumbs up if you can hear me, just so I know immediately that we are all connected, or just pop something in the Q&A channel. Can you hear me? Good. Wonderful. So many thanks to the organizers, and please, based on all their hard work, if I make any sort of errors in the use of technology here, it's on me, not them. They've really done a wonderful job prepping. So for the purpose of this talk, I wanted to get right to the point immediately, as we only have 20 minutes. And my understanding of the audience here are, executives and people who are looking to organize data science and machine learning and AI teams to push their particular business interests forward. And so the fundamental of this talk is that there's a shift going on right now in the way in which one thinks about how data science and machine learning is applied. Whereas previously tools and techniques and platforms were the core of the data science and the machine learning and how you built and did stuff, there's a growing trend that is recognizing the need of some more creative and fundamental skills, the modeling, the creativity that pushes into how one deals with data. And this synthetic data to push the boundaries of transfer learning is very much along those lines. I'm pushing this because it's something of my bias. I'm an applied mathematician by trade and a modeler by discipline. And so this transition is a welcome one to me, because it brings, as the tools and techniques become more refined and more accessible to a wide variety of skill sets, the importance of the creative aspect comes more to the forefront. But let me talk about it in two parts. So first, the synthetic data. So the synthetic data, when I brought it up to, so I work on Metabolon, which is it's a high science company which was built on the technologies which detect metabolites, which if you go out to and get your physical done, you will get a blood sample taken and you'll see cholesterol and sugars and a whole bunch of other stuff. That's what we do, except thousands and thousands and thousands of them. Anyway, when I bring up synthetic data to the folks that work in the lab, and if you have folks, you may have this reaction as well, it's an anathema to them. Their perception of data is that it's this immutable truth. It's like if I said true lies, or perhaps lied truths. The words don't necessarily even go together. But if we delve a little bit more deeply and maybe put our statistician hat on, everyone's aware of variability in data, sampling distribution errors, measurement errors, all sorts of considerations that have us question the absolute truth of the data which are underneath. But that doesn't stop us from using them. And that's really the purpose. So we understand that data gathered through almost any means can be useful in an appropriate context. Synthetic data is no different in that regard. We want to use it to make inferences, but only when it's useful. We don't expect it to be complete truth, but we want to make it useful to get utility out of it. And so let me talk about a few instances of that. So one which almost everyone in the room I would expect to have seen at this point at one time or another is the use of GANS, Generative Adversarial Networks. And so when we think about GANS, and if this picture doesn't freak you out, I don't know what to say. The takeaway from them is that is the generator. The output of GANS is the generator. And so if I just I can't seem to zoom in or right on the screen, but if you can imagine my mouse is hovering over the generator here. What's going on? So we have real images in the green box. For instance, if we're doing trying to generate an adversarial network that will produce fake images, and we're pumping those in, and we have a generator which is taking in, let's just say for the sake of argument, randomized data, and is pumping out something which has the same shape as an image. And I mean shape in the way of data, same data shape as an image. Then we're pushing both of those things as a training data into a discriminator, and the output of those, that really, you can think of that as a classifier for all intents and purposes, and the output of that will inform the generator to get better. So the generator is trying to fool the discriminator is trying not to be fooled. There are all sorts of complexities and innovations in how one does this efficiently and robustly, but that's really the point. The output of this, though, is that you get a generator which can produce things that you're trying to make stuff good enough to fool you. So that's really quite novel. There was a, you'll see I will have included in many of these slides links, mostly because the talk's not an hour long, and so I can't delve into all the details, but please feel free to go through them and see in greater detail kind of what's going on with this sort of stuff. Okay, so everyone's familiar with GANs. There's kind of a lot of work and infrastructure required to build these things and to get the product that is the generator out of them. And so I would understand if this is not necessarily the place where you wanted to push your work, but this is a great example of synthetic data being generated. Another modern innovation is physics-based synthetic data. So this is saying, okay, great, GANs are awesome, and I can shoot in random data and come up with something that is really quite novel, and in many instances, I seem to be able to produce remarkably close things to the truth. But perhaps we can layer on some other aspects which can do better. And so these pictures are credited of rendered.ai. This is a company that, I don't work for them, but this is a company that is using physics-based synthetic data to produce, in this example, images. So you can see in the upper left, there's a real image of an AWAC. What you'll notice immediately about that plane is that has the disk on the top. This is actually it's an innovation that's been around for some years now that helps detection of planes and other things that would try to avoid detection by going below the range of conventional radar. Not everyone on the planet has these, and it is in the interest of several entities to know where planes like this are. And so you immediately run into the very common issue of, well, we don't have enough kind of training data if we wanted to write some detection algorithm and are fortunate enough to have satellites in the sky that might look for these sorts of things. But there are a variety of sensors in which we might use to locate them. Obviously, people know what IR is. You see in the upper right a general synthetic representation of an AWAC, and in the lower right is SAR, which is synthetic aperture radar, if you haven't heard of that. So what are kind of the core ideas here? Well, you have the basic photorealistic effects. You want to have shadow and depth, and you can see those things in the synthetic in the upper right. We will have the physics-based thing of different sensor types, which have different considerations for how we represent these objects. But the one that I want to focus on and kind of really call out is procedural generation, building structures, landscapes, etc. Quick thumbs up or note, anyone ever play a game called Skyrim? I would be a little surprised if no one in the room did, given our technical bent. Thumbs up for Skyrim, or are we don't get to play games anymore? No Skyrim. Okay, bummer. In any case, it's a video game which has an open world. So I naively at one point thought that the manifestations of things like grass in that world must have been rigorously programmed by some horrible intern job where they would one at a time make this beautiful blade of grass, which would respect things like wind characteristics and light and shade and shadow. But that turns out not actually how those sorts of things are done. They're done through procedural generation, which is to say you make a block of a thing and figure out a way to randomize and implement it on a larger scale. And so these build your small physics-based component and then generate it across your area of interest randomly. And so those same principles can be used in the generation of physics-based synthetic data, which is just an interesting kind of call out on how you might scale things if your concerns are physics or physically based. Let's look at one more case study where we are putting our statistics hat on. And this, of course, is relevant to some of our modern concerns. So this was put out by Unlearn AI. I put the link to the blog on top and found it novel enough that I wanted to include it here. The basic problem that is being discussed is one of bringing populations to trials, to drug trials. And as you might expect, during pandemic world, it's a little more difficult to get people through the door to be trials for drugs. And so this company puts forward an interesting solution, which is to say that we have enough data that perhaps we can supplement the control population of a drug trial and thus empower or raise the power of the statistical analyses that are required for these trials to go forward. I'm a Bayesian, and so like some of that doesn't really make sense to me at an intuitive level, because I just think of as you get more samples, you grow more confident in the thing, or at least in the result. But in any case, this is a very novel thought to me in that we say we have enough understanding of what we expect the control population to look like. Can we generate a synthetic data which will be representative and still give us productive information towards the study of interest? So check this out. You'll get some more depth through the blog, but it's another way of kind of thinking of synthetic data being generated for utility and statistical analyses rather than maybe a traditional machine learning application or approach. Second part of what I want to discuss is transfer learning, and so I'm right on time at 10 minutes. So philosophically, this idea has been around forever. I mean, fundamentally, I have a 5-year-old girl and a 7-year-old boy, and transfer learning occurs all the time with, as you might imagine, varying degrees of success. But even on the more technical side, transfer learning occurs even at the very early levels of education, though what you see here is probably, advanced high school or early college stuff. Thumbs up for anyone who knows any of the equations that you see here, especially the ones in the bottom two. Any familiarity with those? First person to tell me what the second equation is, you'll get a thumbs up from me. Show it in the chat. Nobody in the chat. Oh, you cannot see the slides. That is not good. Boy, that is right. Okay, thanks very much for that. I am going to sort out how to share this for you because there was so much good stuff. Obviously, the slides will be shared by the organizers. Oh, slides were on the screen. Okay. So yeah, now they're gone. Okay. Great. Apologies for that. So the slide I was talking about, let's drop the me asking you what they are, and since you had to wait, let me just tell you. So what you see here, obviously, on the very top right is a second-order differential equation, which is the machinery of stuff. And if you're lucky, maybe your instructor told you a little bit of how to think about it. But in the terms of transfer learning, once, and this is for engineers in particular, you get to different interest areas. So you see an equation which is representing an RLC circuit, and below that is a mass damper spring or mass dashpot spring, which probably depends on whether Z is Z for you or not. But they all have the same form. This, in essence, is transfer learning. So it's saying that we have a concept, we have a model that, and based on how this works, can we apply that model usefully to other situations? One a physical situation, one an electronics, a circuit situation. Now, is this correct? Well, strictly speaking, of course not. I mean, the resistors and the springs, for instance, are very nonlinear in many circumstances based on materials, temperature, just to name two possible factors. And so like these equations, they kind of hold. That is, they are useful for how we might think about these systems, but you can build on from there. Much the same sort of philosophy goes with transfer learning. If we go to so-called classical transfer learning, which is modern, and so we're really talking in the last 10 years now, there are a bunch of wonderful applications, and let's say Give me a thumbs up if you have seen the slide switch to modern, just so I know that we're all on the same page here. Good, thanks. And I apologize for what must be now an 8-second delay of pause while I waited for the thumbs up. Bummer. So this is a really nice example. If you haven't read this article, I linked to the one on New York Times. It's based on work that Jeremy Thomas and his company Analytica has done. Most recently, you probably know Jeremy Thomas along with Dr. Jeremy Howard along with Dr. Rachel Thomas from Fast.ai, a wonderful site where their theme is make neural networks uncool again, or something like that, because their philosophy is that everyone should be able to apply these sorts of tools. And so they try and build machine learning libraries that will support that. But for the purposes of transfer learning, this is one of the examples that got some really early hype. So Jeremy Howard went out, took a bunch of visual examples, a bunch of photos and such, and trained a deep network, and then applied it to only 1,000 examples of lung cancer diagnoses. Then he successfully tested it on, I believe, roughly 6,000 examples, and found that its accuracy was 50% or something like that better than what you'd expect of already very good professionals who would examine these data. And so this is a stark example of success in transfer learning and got a lot of people's attention. The model for transfer learning is exactly what you see on the right. So we have some classifier training, we have some feature learning, but we have a large public data set, let's say, of something that is somewhat like the thing you want to learn about. And we use this to train a deep network, and then just in those last couple layers or last layer, we do a little refinement training on your smaller actual data set of interest in order to produce the results that respects the characteristics that were learned from the prior instance. That's kind of classical transfer learning. And so now we're getting to the punchline. I suggest that we take things one step further. And so I labeled this as the future, but the future in this particular case is now. You will see that in the links, I've left 3 links on the right that give you 3 different instances of people approaching this problem, and I'll get into that just briefly. But the short story is there's no reason that we need the large public data repository and couldn't use instead generated high quality synthetic data. So the point with the transfer learning, with this deep learning and then transfer learning over, is that we have something that is like, in some sense, the thing that you actually want to learn about. Why not go and design that yourself? This is where the modeling, the creativity, the intuition can be a real driver for success in this area. Just to give 3 examples. So the deep domain adaptation in computer learning, which is the first link on the right, talks about like the instance of looking at computer vision and takes as a case study New York City driving versus Paris driving. If I trained the car to drive very well autonomously in New York City, it may share some characteristics of what it is like to drive in Paris, but for anyone who's been there, it is not entirely the same. And so the suggestion here is to use true data and then reweight those source samples, to go and modify your true data such that it is more similar to the desired test distribution. What's the minimum threshold for sample size of these methods to work? I'm not sure I would give one. What I would just point out is that the assessment techniques are fairly robust, which is to say you will know based on how the assessment, based on the assessment of your machine learning approach, whether you were successful or not. If you're generating high quality synthetic data, there's not really a threshold on how much you could generate. That's the whole point. You can like dump that. You get your own big data yourself. And then based on the assessments in your transfer learning, you'll know whether you were successful or not. People have talked about success with very few numbers of samples. But again, being a Bayesian, I'm more confident the more data you give me. But if you prove to me, and this brings me to my second and third links, if you prove to me that the distribution on which you are training is sufficiently similar to the distribution on which you are transferring to, then I'm more likely to believe the results of successful transfer learning given small, true data sets. And so that's one of the core issues, well, the core challenges in synthetic data generation for deep learning is that core issue of, is your training set, is your dev set similar to your actual testing set in some meaningful way? And so here's the punchline in the end. statisticians, applied mathematicians, even if you haven't done any machine learning, and I know statisticians are a little upset because machine learning was a bit co-opted because they knew it was hot before it got there. Even if you haven't got into it, you're back in the game now, because figuring out how to generate assessments for assessments between distributions and figuring out how to do appropriate modeling is the core of those disciplines. And so they will provide even more utility in a future where synthetic data drive deep learning and drive transfer learning. Many kind thanks for your attention. I would love to chat afterwards and take some questions, but I understand there are other speakers, and so I don't begrudge you going on to those next topics either. Apologies for the technical difficulties in the middle.